Are you ready? We're on our last conic section. It's called the hyperbola. It's a double-branched apparatus here. It's if you cut your double cone structure vertically, you'd get two branches worth of curves. Not really parabola-shaped. It doesn't have the same properties, but a similar looking shape, so a hyperbola. Hyperbolas, you're going to see those in different places in the world. If you don't quite go into an elliptical orbit, then you're going to sort of slingshot around in a hyperbola curve. A hyperboloid is if you rotated a hyperbola 3D style. That's a nuclear cooling tower. Anytime you have a cone-shaped thing that intersects something flat, like a light would shine out in a cone shape, but intersecting the wall, we would get a curve, and that's a hyperbola. Let's talk about hyperbola equations. They look a lot like ellipse and circle equations with the x squared, the y squared, and the 1, only there's a minus in the middle. And hyperbolas have their own set of properties, just like parabolas and ellipses, but honestly it's a little complicated, so I'm just going to start by showing you how the equations work. So this first one, let's just make up some numbers. Let's say that this goes over by 3 and back by 3. Those would be considered the vertices, and so just like on an ellipse, we would put a 9 under the x squared. Now you'll see this funny box in the middle, not really part of the graph, but it helps us see these dotted lines, which are the asymptotes. This is the only conic section that has asymptotes. So it's sort of that box that helps us determine how wide these things will open. And so the box we're going to use a lot. So let's say this box goes up 5 and negative 5. That just means we're putting a 25 into the equation. Now for hyperbolas, this could open up and down or side to side. So that's the other form that I'm going to show you, if this opened up and down instead. The only thing that changes, you can see, is that the y squared comes first and the x squared comes second. So you check on your notes and make sure that the y squared comes first for an up and down. Now this sort of has the same asymptotes involved. It's still going 3 and up 5 maybe, but since it's opening up and down, we're going to put the 25 right here and the 9 right here. Hyperbolas, too, just like parabolas, are going to have foci in the dishes. They don't work the same way. It's not going to work well for our golf course because there's different properties on this one. But it still does have foci, not with so much bouncy properties. But the foci are going to be found using the actual Pythagorean theorem. And so we would do the vertex numbers squared. So 5 squared plus 3 squared equals c squared. And that comes out to about 5.8. The square root of 34 is about 5.8. And so our foci would be at 0, 5.8, and 0, negative 5.8. Sort of sitting right in there. Let's do some more examples. This one is set up so that there's not a 1 over here, and we need to fix that. So I'm going to start by dividing everything by 36. And let's reduce 4 over 36, 1/9, 9 over 36. Now it's set up in more of a standard hyperbola form. You can tell it's a hyperbola because of that minus sign in there. It's the only one that you're going to see a minus sign. The plus would be an ellipse. If only one of these was squared, then we'd have a parabola. So let's start out. So we've got a vertex number of, looks like 3. So we're going to go to 3 and negative 3. And for the up and down, we're going to go to 2 and negative 2. Now instead of making an ellipse like we did before, that's just the way that we're going to figure out where that little imaginary box goes. And the reason the imaginary box is important is because if we connect the corners, that tells us the slant of those asymptotes. So let's draw in those asymptotes. And that's going to sort of be our guidelines for when we draw this hyperbola, is those asymptotes. Might as well write the equation for the asymptotes. It's a y equals mx plus b equation. Both of these asymptotes are passing through 0, and that's because the only hyperbolas we're going to work on are the ones centered at 0. So all of the asymptotes are centered, and then this one goes up 2 over 3, up 2 over 3. So my first asymptote has an equation of 2/3 x plus 0, mx plus b. The other asymptote, also starting at 0, goes down 2 over 3. Down, nice symmetry there. We're going to see that every time. So this one has a slope, goodness, of down 2 over 3. So our two asymptotes. Now we're ready for the real deal. We are ready to draw our hyperbola. This one happens to open, the x squared comes first, so it's going to open side to side. So we're going to find those two vertex points. And again, just following those asymptotes as a guideline for how wide to make this. That is our hyperbola. If we wanted to find those foci, we would be all a squared plus b squared equals c squared, so 3 squared plus 2 squared equals c squared, so whatever the square root of 13 is. I got you. Square root of 13 is 3.6-ish, so again, those inside the dishes, so 3.6, pretty close there. And negative 3, I kind of had it out there. Negative 3.6 and 3.6 for our foci. Let's write that down. So our vertices, we're at plus and minus 3. And our foci, at plus and minus, I'm going to write square root of 13. Our first hyperbola. You demand more. Let's do another. So this time we've got vertices at 0, plus and minus 4. Is that up and down? So we're going to go up to 4, down to negative 4. The co-vertices are bigger, which might throw some of you off. The co-vertices are at 6 and negative 6. If this were an ellipse, we would not be calling those the co-vertices. So why are they calling those co-vertices on our box? They gave us enough information to make our asymptotes. Did you figure out why they called those smaller ones vertices this time? So we're going up 4 over 6 for those asymptotes. So, another 2/3 x and negative 2/3 x. I guess I could have done plus or minus. Let's start our equation. So, is this going to be an x squared or a y squared first? How can you tell if it's opening side to side or up and down? That is why they called the smaller one the vertex, because this happens to be an up and down hyperbola that's pretty darn wide. And so that's a weird thing about hyperbolas, is the vertex could be smaller. So since this opens up and down, I know I'm going to start with my y squared, my minus for hyperbolas. And then the up and down was the 4. The side to side was the 6. So there's our equation. I guess we should find our foci. This time the foci are going to be on the y-axis because they have to be inside the little dish. So a squared, and honestly it doesn't matter which one you call a, but technically I suppose it should be the 4 squared plus the 6 squared equals c squared. A squared plus b squared equals c squared. Alright, oh goodness. 16 plus 30, goodness, 16 plus 36 and the square root of 52, 7.2-ish. Oh wow, okay, so 4, 5, 6, 7, those are way up there. Are you thinking? I'm thinking that that means that when we move those foci away, did you notice how wide this hyperbola was? So as we move the foci farther away, I think it's wider. Alright, a couple more. So this one has vertices at 3 and -3, x-axis style. And it looks like we want our asymptotes to go up 2 over 1, up 2 over 1, up 2 over 1. And down 2 over 1. Did you notice where that got us box-wise? Because I know that this needs to go out 3. So if I'm going to hit it correctly, wouldn't it have to be up at 6? Is that right? Up 2 over 1, up 2 over 1. I'm going to wind up being up at 6 by the time I hit the asymptote at the corner. Now they call those vertices, so that means there's actual points there. And this is also sort of a wide open one, hitting at those vertices. Opening side to side tells me I want to start with my x squared, minus for hyperbolas, and I went 3 and 3, so 9, and I went 6 and 6, so 36. I'm going to skip foci because I want to get to this last example. Alright, it's definitely side to side, so I'm going to start with x. I know my vertices are at plus and minus 1. And it's hard to tell where the asymptotes are slanting, so I'm not going to guess because I'd probably screw it up. But I do know that there would be a 1 squared under here, and I wish I knew what went under there, because that's the only thing I'm really missing, is I need to know how tall that box is, so that I could have this number, and so I could figure out the asymptote slant. So I think the key here is going to be this information. They gave me an x and a y that work in this equation. So just temporarily I'm going to plug in my x and my y into the equation. So -3 squared would be 9. 2 squared would be 4. I'm just going to call this b squared, I think. And so that's the only thing that I need to figure out is what goes on the bottom right there. Let's see what we can do. So we've got 9. If I subtract that over, I'd have -4 over b squared. 1 minus 9 is -8. Should we do some fancy cross multiplying or whatever you can think of? So it's looking like my b squared is going to be 1/2. So a 1/2 goes down there, which is kind of weird. That means that how far up and down does the box go? We'd actually, remember, have to do the square root of 1/2. The square root of 1/2 is about 0.7. So the box goes up to the square root of 1/2 and down to the negative square root of 1/2. And that's where our asymptotes were. So those asymptotes went up square root of 1/2 over 1, up square root of 1/2 over 1. It's kind of awkward, but the slope then would be square root of 1/2 over 1x